This is the second in a series of videos about the equilibrium constant. In the last video, we learned about what the formula for equilibrium constant is and how different it looks for pressures or for concentrations. And in this video, we're going to talk about what happens to the K value when you manipulate the reaction that it is paired with. And we will start on the appropriate page. Okay, so here's the reaction we're going to be talking about. Carbon dioxide gas plus carbon solid goes to 2 carbon monoxide gas. So let's write the K expression for that. And we'll do Kc because not all of these have to be in partial pressures. So we've got CO is our product. So concentration of CO to the second because of that coefficient. And CO2 gas is a reactant, and then carbon solid is also a reactant, but pure liquids and solids are left out. So we'll just put ×1 for that one. Okay, so what if I wanted to modify this equation? What if I wanted to modify it by multiplying it by 2? This is something we've done in the previous chapters. So we would have 2 CO2 gas plus 2 carbon solid. And this one would become 4 CO gas. So let's write the K for this new expression. We'll call it K prime, and see what that one looks like. So we're still going to have CO on the top as our product, but there are going to be 4 of them this time. So we'll use a 4 superscript. And we still have CO2 on the bottom, but there are 2. So this one has a superscript of 2. There's also 2 carbons, but we don't include pure solids or liquids. So that one is still just a 1. So we have this new value for the equilibrium constant, but look at how these two are related. It looks like we could probably write a relationship for those two. Because CO to the 4th is the same as CO to the 2nd squared. And CO2 quantity squared is the same as CO2 to the 1st squared. So if we take this entire fraction for the first one and we square it, we end up with the equilibrium constant for the second one. So the equilibrium constant for the second one, where it was multiplied by 2, equals the equilibrium constant for the first one to the second power. So when we multiply by 2, we square the equilibrium constant. So this is different than we did in the past. So we don't just multiply, we actually take it to that number as the exponent. All right, let's try another one. So we did, if we multiply, what happens if we divide? If we want to divide the coefficients by 2. I think that dividing is just the same as multiplying by a fraction. So it's the same as multiplying by 1/2. And I think that's easier to think of. So 1 times 1/2 is 1/2 carbon dioxide. 1 times 1/2 is 1/2 carbon. And 2 times 1/2 is 1 carbon monoxide. I didn't technically have to write that one. Okay, so the equilibrium constant for this one we'll call K double prime. And so the same rule applies here. When we multiplied by 2, we took the equilibrium constant to the second power. So when we divide by 2, it's the same as multiplying by 1/2. And when we multiply, we raise it to that power. So when we divide by 2, we raise the initial equilibrium constant to 1 over that number. Or we multiply by 1 over that number. Okay, so here's our first relationship. Multiply by 2 raised to the second. Here's our second one. Divide by 2 raised to the 1/2. And I'm sure the question in everybody's mind is what happens when we flip it. And flipping it is the same as multiplying by -1. So if we multiply that first one by -1, we have the 2 carbon monoxide on the left side, carbon dioxide and carbon on the right side. We can call that equilibrium constant K triple prime, and flipping is the same as multiplying by -1. So if we multiply the chemical equation by -1, we raise the equilibrium constant to -1 exponent. So if you can reduce it down to a multiplication, you can figure out what it is. So these are starting to remind us of some of the Hess's law problems in the enthalpy chapter, and this next one is really going to remind you of enthalpy. So let's take a closer look and define specifically how they're the same and how they're different. So in Hess's law for enthalpy, we talked about how if we didn't know the enthalpy of a total reaction, we could add together 2 smaller steps to get the total. So we can add 2 steps together and get 1 total equilibrium constant as well. So here in this case, our first reaction is N2O gas in equilibrium with N2 gas and 1/2 oxygen gas. So if we want to write K1, our equilibrium constant, we'll include concentration of N2 times concentration of O2 to the 1/2 over the concentration of N2O. And again, these are all gases. We could write them as pressures if we wanted to. I just like to write them as concentrations. Okay, and then for our second step, N2 plus O2 goes to 2NO. We can write equilibrium constant K2 as the concentration of NO product squared over reactants N2 times O2. Okay, and our goal in this expression was to find the total of these 2 steps and then to find the K expression for that total as well. So if we add the reactions together, we see that some of this stuff is going to cancel. We have an N2 in the reactant of step 2 and in the product of step 1, so that cancels. We have an O2 in the reactant of step 2 and 1/2 of an O2 in the product of step 1, so 1/2 cancels in the products and changes to 1/2 in the reactants for step 2. So our total is going to be N2O plus 1/2 oxygen, and that goes to 2NO. We want to find out what is the equilibrium constant for this one. You could probably hazard a guess at this point, but let's prove it to ourselves and make sure we're right. So if we were to write the K total, just from knowing what the totally balanced reaction is, we would write it as product NO squared over reactants N2O times O2 to the 1/2. All right, and now if we compare what we have for K total to the Ks that we wrote for K1 and K2, we clearly are not going to be able to add these together to get that expression we just wrote, which is what we would have done in Hess's law. What we need to do to get from K1 and K2 to K total is we need to multiply them. We're going to multiply the partial steps K values together to get the total. And we can prove it. K1 was N2 times O2 to the 1/2 over N2O. And our K2 was NO squared over reactants N2 times O2. And just as we canceled when we were adding the 2 reactions together, we can cancel when we multiply. So the nitrogens cancel, and the 1/2 oxygen and the full oxygen cancel to leave half oxygen behind. So we have 2NO over N2O, O2 to the 1/2. So we're going to put this in a box because this is important. And we're going to write it out in words. So when adding reactions together, multiple steps, We need to multiply the K values for each step together. This is going to be difficult because this is definitely different than everything we have done so far. Remember what we did a few chapters ago. Compared to Hess's law. In the Hess's law section, we learned that when you are adding reactions together to get a total, we would add our state function, delta H, or delta S, or delta G for each step. And that is not the same as what we're doing here. So when we added the reactions, we added these state functions together. And when we're doing the equilibrium constant, when we add reactions, we multiply the K values together. So these are different. So don't be fooled. Don't forget that the rules for K are different because K is a ratio of products over reactants. And the only way to get products and reactants on the top and bottom to cancel is to multiply them. So we multiply the Ks because they are special. So that's an example of how to use K values for manipulating an equation or for adding multiple equations together. And in the last video, we will talk about different types of equilibrium and about what the size of the K value means.